let's take a look at this next section, which is actually about integration, a little bit beyond the basics. And so we'll kind of explore some strategies around integration or simplification or some algebra that we could do in order to actually get back to utilizing our basics. So when I talk here about integration, the basics plus slightly beyond, I am including substitution. So this is just some more practice for us, getting us set up for lots more integration strategies that will come in the next couple of weeks. Okay, so let's take a look at this first problem. So we have a definite integral from 1 to e squared of the natural log squared of x squared all over x dx. And so we're looking at this and we're thinking, okay, how am I going to integrate this? And I do think that it can be helpful mathematically, shorthand-wise, sometimes we write our squareds like this, but that is that whole logarithmic function being squared. So that is the natural log of x squared, all of that quantity being squared over x dx. So, just simply there's one of our strategies kind of beyond just kind of basic integration, because obviously this isn't just a basic integral here. This isn't one of our basic formulas, but we can do a little bit here to get it into a form that will be one of our basic integrals. So it helps to see that that whole function is being squared, because now I can do some substitution. If I let u equal that function that's being squared, the natural log of x squared, when I take the derivative, and I will also separate the differential at the same time, I would get 1 over x squared times the derivative of x squared, which is 2x. Separate the differential, I get dx. So du is actually 2 over x dx. And I have a 1 over x in my integral. I've got the natural log of the quantity x squared, all of that being squared. I got a 1 over x and a dx. So if I just divide both sides over here by 2, or multiply by 1/2, I'm going to change to red again, I would get 1/2 du equals 1 over x dx, and I can make that substitution here. Got my u, got my du. Actually, I have 1/2 du right there. Better adjust for that constant. And so this becomes the integral of u squared times 1/2 du. Now, as I was doing that, I did drop my bounds. And so let's just recall, with a definite integral, I can also change the bounds. So if x equals 1, when x equals 1, I'm going to come down here and give myself a little more space. When x equals 1, then u equals the natural log of 1 squared, which is just the natural log of 1, which is 0. And when x equals e squared, then u equals the natural log of e squared squared, which is the natural log of e to the fourth, which is 4. So I'm going to change those bounds to u equals 0 to u equals 4. Now that 1/2 is just a constant, so I could even pull that out to the front, and we're taking the integral of u squared du, and now we're in basic. We had to do a little bit of substitution. We had to think of how the function was written, defined, and pick the appropriate u and make the appropriate substitutions. But this is what we've been doing. We've been working with substitution problems of this nature since the beginning of this course. So just more and more practice here as we get more familiar and comfortable with integration. So here we're just, now that we've done all that substitution, now we can just integrate. This is 1/2 u to the third over 3. And I don't have to go back in terms of x because I've converted my bounds into u's. So I've got 1/6, 1/2 times 1/3, and then I've got 4 to the third minus 1/6 times 0 to the third. So that's actually 64 over 6, or 32 thirds would be my answer for this first integral, since it was a definite integral. Okay, let's keep going. Let's look at another problem. What if we had a problem like this? So we've got 1 over e to the x plus e to the negative x. And if I'm thinking about trying substitution, if I tried that entire denominator for substitution, I get stuck because I don't have anything that looks like the derivative. I don't get anything that looks like du. So that's not going to work. But I do notice here that there's a little algebra manipulation. So I'm going to do a little bit of algebra. I'm going to do a little bit of factoring here, manipulate this, get this into a form maybe that I can work with easier. So I see that e to the negative x, and if I factor an e to the negative x out of both of those terms, so remember when we factor it out, we're dividing, it's like dividing by e to the negative x. So when I do that, this becomes e to the 2x and plus 1 dx. And now that e to the negative x, now that it's a product in the denominator, we could move that to the numerator. So that would become e to the x in the top dx. And in the bottom, I'm just going to reorder it 1 plus, and I'm going to write it e to the x squared. So why would I do that? Well, I did that so that we could see the substitution, because if I rewrite that, remember when I did that factoring, we very conveniently ended up with an e to the 2x, but that is a perfect square. So I recognize there that when I factored out that e to the negative x, that this became e to the x squared. And I rewrote it that way on the next line with the integral, because now I can see a nice little substitution. I could say, let's let our u be e to the x, and then my du is just e to the x dx, and I have all of that in my integral right here, so I can make the direct substitutions. This becomes integral of 1 over 1 plus u squared, and then the e to the x dx becomes du. And I have a nice integral formula there. That is my inverse tangent of u plus our integration constant. Just as a quick note, if you prefer, I'll write it in red. If you prefer, you could also use the terminology or the notation arctan of u plus c. So whichever you prefer to work with, arctan and inverse tan are the same thing, just different ways to express the same function. U was e to the x, so let's pop it back in there, integration constant, and of course if you were working or prefer the arctan notation, and I do work interchangeably between those two, so either of those two would be the correct answer for this problem. And so this one was one just maybe a little beyond the basics because we had to do a little bit of algebra, right? Here's a nice example of applying some algebra. In this case, it was factoring out a common factor, applying some algebra to simplify. Simplify or manipulate into a form that we could work with, right? However you want to, think about that. But that's what we were doing here. We were working our way through this because at first glance it didn't look like something we could integrate, but with a little algebra it became something we could make a nice little use of and then integrate. Okay, let's keep going. Let's take a look at this guy. And I do have a little recall over there, but I'll keep that off the screen for just a second. Okay, so I look at this function and I think to myself, man, that 9 minus x squared under a square root looks an awful lot like an inverse sine. And I wrote two of our inverse sine functions over here from our integration formulas as a little recall. We know those. We certainly know the first one. The second one we're going to need to get a little bit more comfortable with. Instead of 1 minus x squared, if we have a squared minus x squared, we can use this formula. That is the inverse sine of x over a. That can be nicely proven just using a little algebra factoring out the a squared. And I'll write just the first start of that. This could be nicely proven if we pulled a squared out, we get 1 minus x over a quantity squared and dx, and then this becomes 1 over a times the square root of 1 minus x over a quantity squared dx, and we let our u be x over a, and we can follow this through really nicely because du, let's finish this one, du is 1 over a dx, and so dx is actually a du, so we can make those substitutions, and that becomes 1 over the square root of 1 minus u squared. We have a 1 over a out in the front. We pull this a out to the front, and when we make the substitution on dx, we get an a times du, so these a's cancel, and we end up with the integral of 1 over the square root of 1 minus u squared du, and that becomes the inverse sine of u plus c, which is the inverse sine of x over a plus c. And if we prefer, we could also write that with the arc sine notation. So I didn't actually intend to prove that right there, but I started talking about it and we just I went through it. So that's where that formula comes from. But I want to mention that these are two formulas that we do need to know. We could write the arc sign if we would prefer using arc sign, or we could say inverse sign. Either way, we should be able to work in between those two and know that those two are equivalent ways to write the same function. Um, so I will highlight both of those. Hopefully the first bullet is one that you have memorized and been working with for quite a while, because we have definitely seen that. We saw that back in Calc 1. But in Calc 2, we kind of extend that a little bit and add in the a squared minus x squared. Okay, but that is actually not what we're looking at over in our problem. In our problem, we've got a 2 minus 3x on the top, not just a 1 or a constant that we could factor out. And so what we're going to do on this one, because think about if you covered up the negative 3x, you'd be able to integrate it using the formula we just talked about. And if we covered up the 2 and had just the minus 3x in the top, we'd be able to integrate it because we could do a substitution. So here is a nice example of splitting up a fraction. So here's another strategy beyond kind of the basics. And again, it is an algebraic technique that we're using here. We're taking a fraction where we have more than one term in the numerator and we're splitting it into multiple fractions. So this is splitting a fraction up into multiple fractions, and then dealing with each of those fractions based on their form. So here's another strategy beyond what I would say is beyond just the basics. So here we will integrate. What we'll do is we'll take just 2 over the square root of 9 minus x squared minus, and then we'll have 3x over the square root of 9 minus x squared. Now we are actually going to integrate each of those on their own. So I'm going to separate. When I do this, I'm actually going to separate and pull out the constants at the same time. I'm going to separate this into two integrals, and I'm going to pull out the constants on each of them. So we have minus 3x, but I'm going to pull out the 3, leave the x, of course, in the integral. 9 minus x squared. We can't pull the x out of the integral, dx. And now what I'm going to do is I'm going to look at each one of those. I'm going to pull this up so we have that little formula there for us. I'm going to look at each one of those based on their form. Notice that this first one is that exact form that we just talked about. So that we know is going to be an inverse sign, arc sign. So that's going to become 2. My a in that case, my 9, let's zoom in. My 9 could be written as 3 squared. So my a in this case is equal to 3, and this becomes 2 times the inverse sign of x over 3. There is an integration constant. Technically, there's like a little plus c. So I'll write it like that. I'm going to write it in a different color. I'm going to write the plus c. It turns out when we finish integrating the second integral, we will also have another plus c, and so we're going to join them together as one constant. We could think of this like c1. All right, let's take a look. How do we integrate this one? Because we've talked about how to integrate that first one. That's definitely an arc sign and inverse sign in form. It had that a, so we adjusted for that. But what about this guy? How am I going to deal with that guy? And that guy is going to be a substitution. I'm going to let u, so in this case, I'm going to let my u be 9 minus x squared. And then my du is going to be minus 2x dx. And I have the x in the dx, so x dx is actually minus 1/2 du. And now I can make those substitutions. So I get minus 3, I get 1 over u to the 1/2, and then I'm going to be multiplying by minus 1/2 du when I make the substitution for x dx. And notice that that becomes, I'm going to carry down the rest of this. We've got a little like C1 hanging out there. We've got a positive 3/2 times the integral of u to the minus 1/2 du. I'm going to bring the exponent up as a negative exponent there on the u to the 1/2. And now I can integrate. That's going to become 3/2. It becomes u to the positive 1/2. We're dividing by 1/2, but dividing by 1/2 is the same as multiplying by 2. So we'll multiply by 2, and we will get a little like C2 is what I'm going to write it as. Now, I carried that through just so that, of course, you could see, and I think we're comfortable enough probably working with integration constants at this point to know that when I take two integrals, if I am adding two integrals together and they each end up with an integration constant, C1 and C2, then of course those two constants join together and become just a constant. So we'll just write plus C. You did not actually have to carry, I will highlight it, you did not have to carry the C1 throughout, but I didn't want to just gloss over that on this first one like that, where we separated our integral so that we could do each piece. Each one of those pieces or terms when we're integrating has a constant, but we group them all together and just call it one integration constant in the end. Okay, let's keep going here and put our u back in. So this is 2 inverse sine of x over 3 plus the 2's here cancel, 3, and my u was 9 minus x squared to the 1/2, or we could write that as the square root. So we could write this as 2 inverse sine of x over 3 plus 3 times the square root of 9 minus x squared plus c. And that is my integral. If you would like, you could also, instead of saying inverse sine, you could say arc sine. So you could use arc sine right here as well. 2 arc sine of x over 3. If you would have preferred to write it that way, you could definitely write it that way. Okay, so remember, that one was definitely kind of taking things a little beyond the basics, right? We had to separate our integral into multiple fractions, and then we accomplished an integral on each one of them using slightly different formulas, right? Like the first one we recognized was an arc sine and inverse sine. So we adjusted and integrated using our formulas for arc sine, inverse sine, and then the other one was a nice little u sub. All right, we'll do a couple more beyond the basics in the next video.